Hello YouTube, and in this video we're going to be exploring how to solve nonlinear systems of equations, and specifically using the method of substitution. Not that the method of elimination is not applicable here, it's just that it's somewhat inconvenient when it comes to kind of creating systems with linear and nonlinear equations. So let's go ahead and get started. Take a look at our systems here. We have three of them. Reason being is that system 3 over here, we'll see when we get to it, but kind of looking at the algebraic properties of a system in which there are no solutions to that, okay? And you always kind of want to know what that looks like so that when you end up with some weird answer, you're not like, oh, I did something wrong here. So let's go ahead and take a look at this system in the top left here, system number 1, in which we have our nonlinear constraint is degree 2, so we have a parabola, x squared plus 4x minus y equals 7. And our second constraint there, our second equation, which is our linear one, 2x minus y equals -1. Now, before we go ahead and solve this algebraically, I do want to bring up the fact that recall that when you're solving a system, we are looking for a solution, but not just a solution to the first equation or the second one, but we're looking for the solution to all of the equations in the system. Notice I didn't just say these two here. We mean like if there were 5 equations, the solution to the system, if it existed or if they existed, would have to satisfy all of the equations or constraints in the system. So that being said, also recall that when you graph the, you make the graph of an equation, what you're looking at is a collection of all points, the locus of all points that satisfy that particular equation. So the reason why I bring this up is because if we were to graph all of the constraints, or both of these equations, for example, in system number 1, we would be seeing all the solutions to each of them, but what we're looking for, if we're looking for common solutions, are points that are on both graphs simultaneously, or where they intersect. So as a matter of fact, the first thing we're going to do before we solve the system algebraically is take a look at their graphs. And as a matter of fact, if we go over to GeoGebra here, you can see that I have already graphed both constraints. So I'll zoom out a little bit here, but you notice that our first constraint, that parabola, is here, and we have our second linear constraint, but we're looking for the points at which they coincide. So it seems that this system has two solutions where these graphs intersect. And so what we'll do is, it's always convenient if you have a graphing utility around, but we're going to look for these points at which they intersect. So it looks like -4 comma -7, and if we come up here to the right here, it looks like about 2, 5. So that being said, we're going to come back over here, a little bit of foresight, a little bit of foreknowledge here. We say, well, we kind of suspect that we're going to get -4 and -7 for one of our solutions, and then also 2, 5 for our second solution. There were only 2 in the system. So that being said, let's go ahead and solve this thing using substitution. Now, substitution, recall, means that we're going to isolate a variable in one of our equations and insert it for that variable in the other equation with the hopes of coming up with a single variable type equation. So that is like all x's or all y's or whatever letters you're using. You just don't want multiple variable types. So looking at this first system here, we could isolate the x squared and get that x by itself. That would be in terms of x and y if we do so. We could isolate this middle x, but that would also be in terms of this first x squared and y. We kind of want to isolate one in terms of the other. So in the second equation, we could totally isolate x in terms of y, that is, kick the y over to the other side, or we could isolate y in terms of x. In this instance, it is most convenient to go ahead and let's solve for this y in the second equation. The reason being is because once we solve for that y, we'll have it in terms of x, and we can insert that into the first equation for this y here. And the first equation will be all in terms of x's. So let's go ahead and get this started. So we say subtracting 2x from both sides here. We see that we get -y, okay, that's really important, equals -1 minus 2x. And then if we go ahead and distribute a -1 throughout this, we get positive y equals, I'm going to go ahead and switch these around since addition is commutative, 2x plus 1. So this is the same thing as our second equation, or at least it contains the same variables, different form. What we're going to do now is we're going to take this, of course, and insert it into the first equation. And so we end up with this. We get x squared plus 4x minus, in parentheses, it's very important here, 2x plus 1. And I say this is very important because, of course, we have to distribute this negative out front. So we end up with x squared plus 4x minus 2x minus 1 equals 7. And if we go ahead and combine like terms now, we end up with, finally, x squared plus 4x, sorry, not plus 4x, instead we combine like terms, so plus 2x minus 1 is 7. If we're going to solve this quadratic equation, of course, it would be convenient to set it equal to 0 and factor. So we say x squared plus 2x minus 8 is 0, and from here we get the factors. Since this is a trinomial, a value of 1, we get the factors, looks like x plus 4, x minus 2. So from here, we could say that, oh, okay, well, of course, either x plus 4 is 0 or x minus 2 is 0, but bottom line is we get negative 4, and positive 2. And so like with any other system, typically linear is probably what people are used to when they watch this video, is that we're going to take these two values, we're going to plug it back into one of the original equations. And I just want to point out again, just like solving systems in algebra 1, algebra 2, we can plug it back into this modified equation if we're using the substitution method, because y is already isolated. So we see that we have, if x is negative 4, okay, negative 4, we got to find f of negative 4, and so this involves saying that y in turn is 2 times negative 4 plus 1. Putting it back into the modified equation, we get y equals negative 7, as we said that we should have, as well as, if we plug in 2, then we get y equals 2 times 2 plus 1, and there's our 5. And of course, this is going to be verified again graphically. Look at this, we say 2, 5 is there, and we say also negative 4, negative 7 was there. Okay, so that being said, we're going to try this again. As a matter of fact, I'm going to skip over here to system number 3, and I'm going to go ahead and start by saying this has no real number solutions. Okay, so our job here was to find out what does it look like algebraically when you solve a system with no solutions. So we're going to start with looking at the graph again of these two equations. So I'm going to unhighlight these two here. And insert the equations of this system here. And you'll notice, first of all, try again. Perhaps I have the wrong parabola. Let me check my system here. We say negative x plus y equals 4. So negative x plus y equals 4 is this linear constraint. And then we say x squared plus y equals 3. So x squared plus y equals 3. There we go. So we say this system has no real number solutions, and it becomes apparently obvious here when you look at the graph, they never intersect. Okay, so always good to graph it first. Now let's take a look at the algebra of the matter. So I would say as a rule of thumb, it's easier to isolate a variable in the linear constraint and then plug that into your other equation. And in this case, it would be really easy to solve for y in the first equation and plug that into the second equation. So as far as that goes, we could say then adding x to both sides of that first equation, we get y equals x plus 4. And now we can substitute this into our second equation here and have it all in terms of x. So it follows that we have x squared plus, in parentheses, I can't stress that enough, we say 3, we say x plus 4. And so again, we end up with this quadratic thing, x plus 4 equals 3. We're going to set it equal to 0, so subtract 3 from both sides. We get x squared plus x, plus a non-ugly x, plus 1 equals 0. Now you'll notice in this case, we have a quadratic thing. It's a trinomial, but it doesn't factor. And of course, if you remember from algebra, if you have a trinomial in standard form, that doesn't factor, one thing we could do if it's set equal to 0 is use a quadratic formula. So we have in this case, we need to know a, b, and c. And so we say a here is 1, b is also 1, c is also 1, and of course we know that the quadratic formula, I hope people know this, is negative b plus or minus square root of b squared minus 4ac all over 2a, in which we pay a lot of attention to this value inside this radical right here. It's got a name, it's called the discriminant. Discriminate is a different word. This is a discriminant. Okay. The reason being is because if this comes out to be negative in here, then we know we're going to get non-real results. If it comes out to be positive, then I'm going to go ahead and pursue those things, and that's what I have calculators for. But in this instance, I say, let's go ahead and find b squared minus 4ac first. This is what I suggest to my algebra students. So we say, in this case, we have all ones, kept it simple. We say 1, 1, 1. We say 1 squared is 1 minus 4 times 1 times 1 is 4. We end up with negative 3. So in the grand scheme of things, one could say that our x values are negative, plug in for b1, plus or minus the square root of negative 3 all over 2 times 1. But the bottom line here is that we ended up with a negative discriminant. So this is non-real. That being said, solve a non-linear system, you're going to come up with imaginary numbers. It just means that there are no solutions, no real solutions. So again, let's just go ahead and bury this second system here real quick. We say, and you could turn the video off if you're done at this point, but we say, in terms of which variable it'd be easy to solve for, solve for y in the first equation. This spawns this new equation. We get y equals 2x plus 5, adding 2x to both sides. I'm going to go ahead and substitute this in for y in the second equation. So, again, it's convenient to substitute into the nonlinear constraint or equation. So we say 2x plus 5. Notice that I put parentheses around that, again, because we have to distribute our negative. We get x squared plus 3x minus 2x minus 5 equals 1. And combining like terms, we have x squared plus x minus 5 is 1. And setting this equal to 0, we have x squared plus x minus 6 equals 0. So our two factors happen to be x plus 3, x minus 2, and so we end up with these two x values, 2 and negative 3. And of course, to find the y values that correspond with these, we could set up our ordered pairs at which these two graphs would intersect, negative 3 comma blank. We plug these in, and again, it's really convenient to plug it into this modified equation up here. So we say y is double the x plus 5. Well, in this case, we say y equals 2 times 2 plus 5, and over here we say y equals 2 times negative 3. Negative 3 plus 5. So in this first case, we get, looks like 9. In the second instance, negative 6 plus 5 is negative 1. And again, we can verify this graphically. 2, 9, negative 3, negative 1. Go back over here. So we say 2, 9, 2, 9 up here, and negative 3, negative 1. So hope this helps.